Our group is working on exploring potential solutions to the small-scale problems of the Lambda Cold Dark Matter model. And this is by myself, Michael, Samuel, Anvit, Prahlad, Katrina, and Ashwin. And these are the topics that we'll be covering in today's presentation.
So first, here's an intro to what dark matter actually is. Dark matter is a type of matter that doesn't interact with light or the electromagnetic field. Unlike ordinary matter, dark matter doesn't emit, absorb, or reflect light, making it invisible to traditional telescopes and similar tools that rely on light. Even though we can't see it directly, scientists have estimated that dark matter makes up about 27% of the entire universe. To understand dark matter, scientists use methods like gravitational lensing in studying rotation curves. Gravitational lensing is the phenomenon that happens when dark matter's gravity bends and distorts light from massive objects like galaxies and galaxy clusters. Even though dark matter itself doesn't interact with light, its gravity affects how we see light from other things in the universe. By studying these effects, astronomers could map dark matter in the universe. Another method involves looking at how galaxies rotate. When scientists observe the speed at which objects in a galaxy rotates around its center, they find that the visible matter, like stars and gas, isn't enough to explain the observed speeds. Dark matter is thought to provide the extra gravitational force needed to explain these rotations. By measuring the speeds of stars or gas clouds in a galaxy, scientists can figure out where and how much dark matter is present. And the current understanding of the composition of the universe is based on the Lambda CDM model. According to this model, the universe is primarily composed of 26.8% of dark matter, 68.3% of dark energy, and ordinary matter, including atoms and everything we can directly observe, makes up only a small fraction at 4.9%. Dark matter is believed to be cold and collisionless. Cold in this context means that dark matter particles move relatively slow compared to the speed of light, and collisionless means that dark matter particles do not interact with each other or with other forms of matter via electromagnetic forces, except through gravity. The Lambda CDM model has been successful in large-scale structure and observed features of the universe, but it has some challenges when applied to smaller scales, such as within galaxies. And these problems include the core-cusp problem, missing satellites problem, and the too big to fail problem. Our ongoing observations and experiments aim to refine our understanding of these challenges we face.
Okay. So the Lambda Cold Dark Matter model is the cosmological model that describes the large-scale structure and evolution of our universe. The lambda symbol refers to the cosmological constant. It represents dark energy, which is responsible for the universe's accelerated expansion. This model incorporates baryons, which are just physical matter that compose of protons, neutrons, and other such particles that are made of quarks. Um, the baryonic matter in our universe is responsible for the creation of our universe's structures, such as stars and galaxies. While the baryonic matter is essential for the existence of such structures, the presence of dark matter and dark energy in our universe plays a significantly dominating role in our universe's evolution and structure formation. The Lambda Cold Dark Matter model supports the notion that the universe is expanding with an acceleration of approximately 73 kilometers per second per megaparsec, which means for every megaparsec of distance away from your frame of reference, objects are receding at about 73 kilometers per second. And 1 megaparsec is approximately 3.09 times 10 to the 19th power kilometers. In this cosmological model, we do have dark matter present, which gravitationally interacts with itself and baryonic matter. So while dark energy is causing the universe to expand, dark matter provides an opposing force of keeping structures held together. The Lambda Cold Dark Matter model assumes that dark matter is cold, meaning that it moves at non-relativistic speeds, these speeds being significantly slower than the speed of light. These slow speeds cause the dark matter particles to clump together and form the cosmological structures in our universe under the influence of gravity. However, while the slow speeds of dark matter particles in this model are essential for structure formation, which has been successfully modeled on the large scale, this very property of dark matter plays a role in some small-scale discrepancies between lambda cold dark matter model simulations and astronomical observations. These discrepancies known as the small-scale problems. Next slide. Okay, so Before we talk about the small-scale problems presented in the Lambda Cold Dark Matter model, we need to first address how small the small scale is, and this would be approximately 1 megaparsec or less. Structures that fall under this category tend to be significantly smaller than galaxy clusters, and such structures can include dwarf galaxies, satellite galaxies, and subhalos. So the first problem we'll be addressing is the core-cusp problem, and this is when the Lambda Cold Dark Matter model overpredicts the density of dark matter halos. This disagrees with astronomical observations of dwarf galaxies that suggest lower density profiles. The term cusp refers to the higher or steeper density profile, and the word core refers to a flatter or not as high density profile. So if we take a look at the graph on the bottom left, uh, and the vertical axis of the graph represents density and the horizontal axis represents radius. This is from a 2009 paper by Dr. Antonino Del Popolo, and this paper aimed to specifically study the core-cusp problem. The solid line represents the density profile of a halo that is consistent with the Lambda CDM model, and the dotted line represents a model which is more consistent with observations of dwarf galaxies. We can see how the solid line is much steeper and thus cuspier. The slow speeds of the dark matter particles in the Lambda Cold Dark Matter model make it extremely easy for the dark matter particles to accumulate and clump together while being held together by gravity. So the missing satellites problem is the second small scale problem, and this addresses the discrepancy between the number of satellite galaxies predicted by simulations that use the Lambda CDM model and the number of satellite galaxies that we observe around our Milky Way. So if we look at the graph in the middle, which was taken from an article by Gaurav Kular, in which he summarized a paper published in 2018 that aimed to address the missing satellites problem by analyzing the observations of the Sloan Digital Sky Survey and comparing that with the number of satellite galaxies predicted by the Lambda CDM model. We can see how, if we look at the graph, you can see how there are more predicted luminous satellites in the Lambda CDM model than the number of observed luminous satellites around the Milky Way. And you can look at the key over here. So the Milky Way satellites are denoted by the triangles, and the Lambda CDM model galaxies are denoted by the line. Um, so a strongly believed cause of the missing satellites problem is that we simply are unable to see some satellite galaxies around the Milky Way because they just aren't luminous enough. Baryonic processes such as ionization and supernova explosions also play an important role because they can prevent the formation of stars. And this is because such processes like ionization can make it difficult for gas to cool and collapse. And this cooling and collapsing of gas is necessary for stars to form. The third small scale problem is the too big to fail problem. This problem addresses how the Lambda Cold Dark Matter model overpredicts the mass of dark matter halos. There is a direct proportionality between the mass of a dark matter halo and the luminosity of the dwarf galaxies within it. So the more massive a dark matter halo is, the more luminous or the more bright the dwarf galaxies within it will be. However, observations of dwarf galaxies suggest dark matter halos of lower mass due to the low luminosity of these dwarf galaxies. So if we look at the right, we can see a set of graphs, and this is taken from a 2015 paper which aimed to analyze observations of the local group of galaxies and compare that with Lambda CDM simulations and hydrodynamical simulations. So the main difference between these two types of simulations is that hydrodynamical simulations account for baryonic feedback processes that the Lambda CDM simulations don't account for. So these graphs are plotting the velocity of satellite galaxies against the distance from the center of the halo. The hydrodynamical simulations are on the right, and they're the graphs with the blue lines, and the Lambda CDM simulations are on the left, and they're the graphs with the black lines. The red markings on the graph represent 9 observed dwarf galaxies around the Milky Way. Velocity in this case is directly proportional to mass. So if something is shown to have a higher velocity, then it has a higher mass. We can see how in the Lambda CDM simulations on the left, not only predicts more satellites because there's much more lines than the hydrodynamical simulations, and this alludes to the missing satellites problem, but the Lambda CDM simulations also predict satellites with higher velocities and therefore higher masses than the hydrodynamical simulations, which brings us back to the too big to fail problem. And if we compare both the Lambda CDM simulations and the hydrodynamical simulations, we see that the highest hydrodynamical simulation lines are much closer to the red markings than the Lambda CDM simulations are. Thank you. Next slide, please.
The self-interacting dark matter model represents a promising solution to the long-standing cosmological challenges, including the core-cusp problem and the missing satellites problem. And this model is also considered as an alternative to the Lambda Cold Dark Matter model. In SIDM, dark matter particles engage in both gravitational and non-gravitational interactions, which allows them to scatter and collide. This interaction potentially leads to the formation of a core within dark matter halos, which could help explain the core-cusp problem. And the same interaction suppresses the formation of small dark matter subhalos, which addresses the missing satellites problem. And additionally, SIDM is very unique because it has the unique capability to predict and study the behavior of dark matter using galaxy cluster collisions. Next slide, please. So to talk about baryonic feedback, we first need to talk about baryonic matter. Baryonic matter consists of subatomic particles known as baryons, which are composed of 3 quarks. This matter can be directly detected using scientific instruments and encompasses a diverse array of cosmic components, including stars, gas, and dust. Baryonic feedback could potentially address both the core-cusp problem and the missing satellites problem, as observing dwarf galaxies has provided support for the idea that baryonic feedback can play a role in flattening the central density profiles of dark matter halos, which can alleviate the core-cusp problem. However, this is still a very active area of research, and there's still a lot that we do not know on this matter. Baryonic processes additionally can impact the formation and survival of small dark matter halos, and these processes can impact the formation and survival of small dark matter halos. These processes can suppress the formation of low-mass dwarf galaxies or even cause the disruption of some existing ones, and baryonic feedback therefore provides a mechanism to explain the observed deficit of satellite galaxies.
Who is that? Speak.
I think this is Ashwin. Yeah. Yeah, I can take over. So we can revisit the future direction that we had in our previous colloquium. So basically in our previous colloquium, we wanted to set up we talked about how we wanted to set up initial conditions and cosmological parameters for our simulation of the blood cluster. So these parameters would be the position, velocity, and mass of the baryonic and dark matter particles, and also the Hubble constant, dark energy density, baryon density, and dark matter density. So we'll later see how we did not initially begin simulating this, but we actually worked on a much simpler simulation before working on this. But anyway, so in this simulation that we wanted to work on, we were implementing self-interactions and baryons to simulate SIDM with baryonic feedback. And we also wanted to select an integration scheme to solve the equations of motion in the system. And one integration scheme that we were thinking of is the leapfrog method, which is pretty efficient. And then we would run the SIDM simulation and also run the Lambda CDM simulation and compare those results to see which is closer to astronomical observations.
All right, so now we'll look at the Python simulation that Sakash really mentioned. So we wanted to start with our Gadget 4 software, but that was kind of complicated, so we decided to do a simpler Python code first. This Python code is by Philip Mox, and the GitHub link is there, and it's also in the sources, so if you want to check it out. So anyways, this code it's not too difficult. It first consists of some parameters. So the main parameters are the number of particles in our n-body simulation. We have the total time of the simulation. We have what's called a timestamp, which is basically each little step, and then a bunch of them until we get to the total time. And finally, we have something called gravitational softening, which makes calculations of gravity at small distances more accurate. So initially, all these particles are assigned random positions and velocities, and these positions and velocities are in the form of lists or vectors. Um, and then in our code, we have two main functions. Our first function uses Newton's law of gravitation to calculate the acceleration. And then our other function will calculate both the potential energy and then the kinetic energy. So after each timestamp, or for each time step, the code will calculate the acceleration for all of the particles, and then it will use this time step to recalculate the positions and the velocities of the particles. So these positions and velocities are constantly updated, and they will be put on a graph, which is shown on the top right. So as you can see on the top right graph, you can see like the X and Y directions of the particles. And at the same time, for each time step, the energy of the total system is calculated, and then it is plot on this chart at the bottom, which is shown on the bottom. So our red line means a kinetic energy, our blue one means potential energy, and finally the black line is just a sum of these two energies. Yeah. Next slide, please. Okay, so some of our results. First, we were able to get the code to run, which is good. So initially, we had some troubles, setting up some softwares or whatever. So it was good to see that we all got the code to run. And we tried to do a bit more than just running the default code. We tried to change some of the initial parameters. So first, we wanted to increase the number of particles. So, a normal n-body system might have more particles than just 100 or so. So we wanted to increase at least a couple magnitudes. However, when we started increasing it, we noticed that our simulation speed would become really slow, or our code would frequently crash. So some ways we tried to combat this was trying to make the position graph for all the particles a bit bigger. So, each particle has a bit more space to move. But that did not work too well. So yeah, anyways, nevertheless, this simulation got us familiarized with n-body simulations, and from there we went into Gadget 4.
Okay, so what exactly is Gadget 4? Gadget 4, or Galaxies with Dark Matter and Gas Interact, is a massively parallel simulation code that allows one to conduct collisionless n-body simulations and is written in C++. The n-body refers to a simulation of a dynamical system of particles. I mentioned that this code is massively parallel. So what does that actually mean? Massively parallel processing, MPP, is a form of collaborative processing of the same program by two or more processors, allowing for faster computation. GPUs run this type of process as they have the necessary architecture. This code can be applied to a variety of simulations, like one describing Newtonian or three-dimensional Euclidean space, where particles are described by a set of coordinates and Newton's laws of motion and gravity, or something like a periodic long box, where an infinite system, like the universe, is approximated with a small part, known as a unit cell, and many more types of simulations as well. This allows the simulation of planets, stars, and galaxies to predict their orbits over time. The original Gadget 4 code, the original Gadget code was written in 2001, and Gadget 4 is the fourth iteration of the code, written in 2021 by Volker Springel.
Why Gadget 4? Gadget 4 has an abundance of config options that allow us to simulate our desired situations. For example, parallelization options allow us to optimize the running of the code. In one of the options, for example, you can pin MPI processes to cores in an optimum fashion. In the basic operation of code section, you can specify what dimensions to use, set periodic boundary boxes, and more. The gravitational options allow you to turn on self-gravity and other gravitation calculation techniques. The SPH formulation config options allow you to turn on SPH, which stands for Smooth Particle Hydrodynamics, a method to calculate the interaction of fluids. It treats the fluids as a bunch of particles and then calculates how each particle affects another. It is more computationally expensive, however. You can turn on the tree PM method. It is a way of simulating the formation and evolution of large-scale structures in the universe. It combines two different methods, the Barnes and Hutt tree code and the particle mesh code. The Barnes and Hutt tree code is a method for calculating the gravitational forces between particles in a simulation. The particle mesh code, on the other hand, is a method of calculating the gravitational forces using a grid-based approach. Next slide. Furthermore, the other slide was about compile time config options. During the running of the code, you can specify certain parameters in a .text file. Some of the things you can do is change the file format of the snapshots you receive as the code runs, specify the path to the initial conditions file of the system you are simulating, set the CPU time limit for running the code, do memory allocation, set the simulated time span as well as the spatial area, and finally various parameters for gravity calculations and SPH.
Okay, so what have we done so far with the Gadget 4 simulation? We started off by compiling the C++ libraries that are required for the code and are not commonly on normal laptops or PCs. First one is the MPI library, or message passing interface. This helps to send messages and assists in the massively parallel working mechanism of the code. The GSL library brings about the GNU Scientific Library, which holds numerical computations in applied maths and sciences, such as elliptical and exponential integrals and hypergeometric functions, etc. The FFTW3 library is a fast Fourier transform of the West, which computes the discrete Fourier transform. The HDF3 library, or hierarchical data format, manages, processes, and stores the data from the simulation. The HWLock, or hardware locality library, lets the code know exactly where important hardware or computing elements is in the device that it's being run in, such as the CPU, memory, and input-output devices, etc. And the vector class is used for explicit vectorization and stores elements of a given type in a linear arrangement and allows fast and random access to any of the elements. So we are currently working on making the code using these libraries and running some of the examples already provided in the code. The examples have set parameters that we're testing, and once we do a bit of research and experimentation with those, we can apply the settings for the bullet cluster and run the simulation for that.
So now that we've talked about Gadget 4, what exactly do we plan to go with Gadget 4? We currently focus on simulating 3 example cosmological simulations and analyzing their condition and output. The 3 cosmological simulations we're attempting to run is colliding galaxy SFR, the acronym SFR standing for star formation rates. Santa Barbara PSPH64, acronym PSPH standing for density independent version of SPH, SPH meaning computational method to model flows, and cosmological DM, standing for dark matter, only simulation with IC index catalog creation. Each one of these simulations are different due to the different conditions / parameters giving a different output. A notable condition is the Hubble constant, representing the normalized rate of cosmic expansion, which takes on different values in colliding galaxy SFR with a value of 0.1 and Santa Barbara's PSPH64 with a value of 1. Using this knowledge of cosmological simulation and condition with the help of Gadget 4, will help to set up the initial condition and cosmological parameters such as position, velocity, Hubble constant, dark energy, and more to run the simulation of the bullet cluster. So now that we've explained our goals on Gadget 4, what is our approach towards reaching our goal? We plan to use an integration scheme to solve the equation of motion in the system. This is needed to run the simulation frame by frame. So for each time step, each frame will go to another frame. This is essential for simulating complex physical systems, such as cosmological simulation in our case, that involves particles interacting with each other, where obtaining analytical solution is impractical. With the use of Gadget 4, we plan to simulate the self-interacting dark matter simulation and cold dark matter simulation. Using these results, we'll compare whether the simulation of self-interacting dark matter or the simulation of cold dark matter was more closer to astronomical observation. Knowing which simulation is closer helps figure out which model is more dependable and which one we can use to go forward with finding solutions to small-scale problems of Lambda Cold Dark Matter model.
Yeah, so we would like to thank Dr. McMahon for guiding us in this project and giving us support along the way. We would also like to thank the Computer Science and Engineering Department at ASDRP for providing us with the opportunity and platform to conduct our research. And we would also like to thank you all for listening to our presentation. And this is our references slide, and here's a QR code, so you could also scan it to get access to all our links.